and share screen, ground, share. So the paper for this week is called Dataset Cartography, Mapping and Diagnosing Datasets with Training Dynamics. And their concept is actually very, very, very easy. The main objective of this paper is to assess the quality of the data. Sometimes you have a data set like MNIST, and you get like your convolutional neural network, your network is able to learn how to perform that task well. But some other data sets are very, very, very hard to train on. So what is the difference between them? What makes a data set easy or hard to learn? Can we categorize these? Can we do something with it? And these are the sort of questions this paper is trying to answer. To do so, they measure things during training, which they call training dynamics, to build the map such as this one on figure 1. To build this map, they need to collect 3 variables, mainly 2. The third one, I would say it's a bonus. So variable number 1 is the confidence over epochs. I'll go in section 2, they'll give some details, and I'll wait for section 2 to explain what this is. But you can see this as how confident is the model on the correct class. Then the second variable is the variability. How does the probability in the argmax and the correct class changes as the model is being trained? And the third variable, which corresponds to the colors and to the symbols, is the correctness, which is the percentage of time that the classifier is working correctly for each sample. So giving these 3 variables, you can build this map. And from this map, they essentially categorized 3 regions. So you have your samples in your data set that are easy to learn. So the samples that your classifier can, in a few epochs, just understand them and be able to work with them. On the opposite side of the spectrum, I would say, so easy to learn have high confidence and low variability, usually. Hard to learn have low confidence and low variability. These are the samples that are very, very, very hard for the classifier to ever get it right. And then they categorize the most interesting, the third group, which are the ambiguous samples, which typically have average confidence, but they are not restricted to it. You can have samples with relatively high confidence and samples with relatively low confidence. But the key characteristic is that they have high variability. So as the model is being trained, they change a lot. And they categorize these samples as ambiguous samples. And I have pretty much summarized the core of the paper. So they created this map. With this map, they created 3 regions for your data set. And the second half of the paper is pretty much what can you do with these 3 regions. So in a summary, what they mention here in the abstract is that the easy to learn samples do not contribute that much to what your model is learning. And as such, maybe you can ignore most of them. Maybe using ambiguous and hard to learn samples is the way to go, because you want your classifier to be better. And if he already knows these ones, it doesn't need to learn any more from them. So it just can focus on the other ones. And that's what they will try to find out in the later sections. Meanwhile, let me double check if I didn't forget any key detail. I don't think so. They do most of their experiments in NLP datasets, so language understanding. And they use the Roberta Large classifier. So it's a very, very, very large model with good capability on these tasks. So this paper implicitly assumes that you have a decent classifier for your task. So it is not, the conclusions that they extract here may not be translatable to models that cannot perform well in your task. So keep that caveat in mind. Essentially, what they want to do in the later sections is how to use this map to make your model learn better / faster. And with this, we can jump into the details. Before I jump into the details, does everyone got a grasp of the core idea of this paper? Yes, no? If no one speaks up, I'll assume that that's a yes. Okay, good. So
can I, sorry, if I can make a general comment just to add on what you've said, is that when reading through the paper, I thought it was a very interesting approach, because again, they are sort of drawing focus into how you can improve your model without necessarily playing with hyperparameters. It's more like, okay, look at your data now. And how can you use your data in interesting ways, which I find quite interesting from recent machine learning papers, that they're not just add more layers or, do a massive hyperparameter search, but more like try to be smart about your training.
Yeah, essentially the model learns the data. So if you give them a good data combination, you will probably improve your model. That's the core concept. And so, yeah, it is, as you said. Jumping into the details. So what they call the training dynamics are essentially two very simple metrics. So they lay out the assumptions here. So they assume a deep learning framework with some gradient-based optimization. The data is shuffled, and they train across epochs. Given these assumptions, you can define their what they mention as training dynamics, and the metrics they consider to build that map on figure 1. So the first metric on the x-axis is the confidence. So it is the mean of the model probability of the true label across epochs. So you train your epoch, you collect the confidence, you train another epoch, and so on and so forth. And you can build the confidence for each sample. So it's not.
May I ask you a question?
Yes, of course, Arvid.
Sorry. This number, the confidence, it depends on the epochs, right? So it starts with the epochs at 1. But wouldn't you expect that if you have like a sort of what's called burn-in time, where you train first and then start counting epochs, you might get actually different results?
Yes, they mentioned that in the appendix. They say that ignoring the burn-in time or not doesn't make much difference in the overall conclusions, and the results have a very high correlation. But that is a good point. I think it's appendix A1, if I'm not mistaken.
So it probably should be called an accuracy rather than a confidence. Right? Confidence, you can be confident and wrong. All the time.
Yeah, but so they have they have a caveat here, which is the confidence for the true label. So it's a bit cheating in the sense that they use the label. So this is not you can't extrapolate this for like self-supervised networks, but still it's quite interesting. The appendix, so the figure 6 in the appendix talks about what you just said, Arvid.
Thank you.
Yeah, I think that the main difference so the main point of this is that they're trying to measure how confident the model is exactly on the true label, right? So it's not just, so that they don't really, I guess they would like it to be 100% confident, like they would like a 1 on the accuracy, but they don't really care about the height of that value. Oh no, sorry, they do care about the height of that value, but they don't care about what the others are.
Did they maybe do that because they leave the number of classes open, right? Because if you take something that is not true label dependent, then that measure might become dependent on how many classes you're trying to predict against. Versus this, you're really testing only against the one class you think is right. So that might be a reason.
I think so. The second metric that they consider, but they don't use as much, is correctness. So what is the percentage of epochs for which you classify correctly a given sample? And the last metric they consider is the variability. So it is the standard deviation of the probability assigned to the correct class over the epochs. So taking these three metrics, again, we can build a figure such as figure 2, which is the same as figure 1, but for a different data set. So the data set on figure 1 was SNLI, which is this data set, the standard natural language inference corpus, where you are given an initial sentence and an hypothesis, and then you need to label whether it is a contradiction, whether it is neutral, or whether it is an entailment between these two sentences from the first to the second. The second data set is a data set created by the research group from the paper I'm presenting now. And essentially, they will provide you with a sentence, just as this one. So Robert woke up at 9 a.m. while Samuel woke up at 6 a.m. So he had less time to get ready to school. And the model has to identify what this he means. And he's given two hypotheses. In this case, if it had less time to get ready for school, it has to be Robert, because Robert woke up later on. And if he had more time, then it had to be Samuel. So this is what the we know grant the data set is trying to challenge the model to do. Throughout the paper, they tried to get the idea that the other data set was crowdsourced with not so great quality, and their data set was crowdsourced with better quality. Therefore, they have fewer samples here, but I don't want to get into too many details here regarding these two data sets because I don't know them well and I really can't comment on them. But if you compare figure 1 to figure 2, you'll see that figure 2 has fewer samples here in the hard to learn region and more samples around these transition between easy to learn and ambiguous samples. So yeah, I've talked about the metrics. They also have, they have this correctness metric, which gives the color and the shape to the plot, but they don't use it as much. And down here, you have the density for each of the three metrics. So you can see that there are many samples with very high confidence. And the majority of samples are in low levels of variability, so around this region up here.
One question:
Yes.
Are they actually independent? They are not quite independent, right? So you confidence and variability. If you know variability is or low, then you know that confidence must be either very high or very low, right? It's
yes. If variability is close to 0, they have by necessity they have to be either up here or down here. And if variability is very high, they have to be around here by necessity. Yes.
It's a bit unfortunate. If you want to have a map, you ideally want to have the axis independent as possible.
So you can use like the full map. So in this case, you have like a I don't know how to describe the
parabola sort.
Yeah.
So there's an edge case here, which is towards the upper right. So because they're measuring variability within epochs, right?
Yeah.
So there is, I guess it is an edge case. It's not very common indeed. You don't have anything on the top right where the model is very confident, but it constantly changes from one prediction to the next, which is what you would call the completely ambiguous example.
Yeah, but then it wouldn't be confident. It would be confident half the time. So that would be probably a middling confidence, wouldn't it?
No, because they measure confidence as the max, so as the value of the softmax. So you can imagine a case where if an example is half the, so if you have the same example repeated n times and half of those times it has one label and the other half has the other label, then depending on how they are shuffled, you can have the model learn in one epoch the first label with high confidence, and in the other epoch learn the other label with high confidence. So I think that's what they mean with variability and confidence.
Yes, so the confidence would be a half then, right?
Yeah, because confidence is only for the correct label. So
yeah, but it's in the epoch. So it's at the end of the epoch, you measure the confidence for the correct label. No?
I don't think so.
Because each of these points is one example, right?
Yeah.
So if each point is one example, if at the end of one epoch you have high confidence in one class, and then in the next epoch you have high confidence in the other class.
Yes. But only one of the classes is correct. So for the for one of the cases it will be 1, and for the other case it will be 0.
Oh yeah, okay, yeah, I understand now. Okay.
I forgot to talk about one detail in page. I think it's up here. Okay, yeah. So they have this footnote where they define what out of distribution and in distribution sets are. This will be relevant for the remaining of the paper. So they theorize that if they do things right, they will increase the generalization capabilities of a model, and they could measure the generalization capabilities of a model through an out of distribution test set. In this paper, an out of distribution test set is a test set for the same task, but that belongs to another data set. So in both examples, sorry, the zoom thing appeared up here, and now I can change tab. Maybe I can. Okay. So this data set that they created, the Wino Grande, is essentially the expansion of some other original data set called, I think it's WSC, which means Winograd Schema Challenge from 2011, and the Winograd is from 2019, if I'm not mistaken. Yes, 2019. So both data sets essentially try to answer the same type of questions, but they were collected by different people in different instances. So this is what they categorize as out of distribution. So same task collected in different time by different people. I think this is an important point to make, because in some papers, out of distribution could mean things for a completely different task. And in this case, it's for the same task. Moving on. The next thing I would like to talk to you about is this table 1. So they theorize that the hard to learn examples could correspond to incorrect labels, and they provide a few examples. So if you look at this example, then it is clear that this example is incorrectly labeled. So Amy's handwriting was meticulous, while Cynthia's handwriting was often sloppy because X was careless about their work. From this sentence, you would say that Cynthia's was careless about her work because her handwriting was often sloppy. However, the correct label, according to this dataset, is Amy. So they essentially gather a few examples where what they theorize could be true. However, I would like to put in a pinch of salt and keep in mind that these could be cherry-picked. So I think this is a very bold statement, and there are not enough proof to confirm this. However, I think it's a very strong theory, and if you had to start looking for incorrect samples somewhere, I would start here as well. I think it's a solid argument, but it's very hard to prove. Similarly, they theorize that ambiguous samples corresponds to samples that where the answer could go either way. For instance, in this example, Kayla dated more people at once than Betty because X was in an exclusive relationship. I would say, if it was me labeling this example, I would say that the correct answer would be Betty, but it is debatable. Are these two things necessarily correlated? Probably not. And as such, the model could also be confused the same way as a human could be confused. So yeah, they say that as soon as you build that map, you can start looking for incorrect labels using the hard to learn examples, and you can find ambiguous examples in the ambiguous region. And they will use this information to play around with the original data set such that you can build a subset that is better for your model to learn for the in-distribution task, which is the test set of the original data set, and the out-of-distribution task, which is the test set of a different data set, but for the same task. With this, we get to section 3, where they start playing around with this. So they build a relatively simple experiment. They create multiple subsets of the same data set, they train a model, and then they compare the results. To do this, they first create 2 baselines. Baseline number 1 with all of the data, so 100% of the trained data, and baseline number 2 with 33% of the data sampled randomly. Then they go to their map up here, and they start slicing this data set. So they can slice vertically and get the samples to the right. So the samples with high variability, they can slice vertically and get the samples to the left, samples with low variability. They can do the same for confidence. They can also do the same for correctness, but they don't, the interesting results are not here. So I would like you to pay attention to the following subset. So the subset that contains the easy to learn samples, so high confidence, low variability. The subset that contains hard to learn samples, which is low variability, low confidence, and the subset of the ambiguous sample, which is high variability and whatever confidence. And if you look at table 2, which compares the results, they also compare against other papers. You'll see that for the Winogrand dataset, using a subset with ambiguous samples is almost as good as considering 100% of the samples, and it's much better than sampling randomly. Interestingly, the datasets with high confidence, so the upper left of the map, have very, very poor performance, while the subset with hard to learn samples, which is lower left, got almost as good results as ambiguous. If we look at the out-of-distribution set, we see that the ambiguous subsample subset has better performance than 100% train. This means that you can use less data to get better performance. So this seems to be a very, very strong statement. And you get the bonus that this dataset was never seen at training time. So they argue that using the ambiguous subset will generate a model that is more generalizable, because it doesn't necessarily fit to the particulars of that dataset, but it behaves better in an outside dataset for the same task. They also compared against other papers. The other papers did not have as good results, but I would say that the main conclusion from this table is that if you use ambiguous samples, you'll probably get better results with a third of the training time, which, to be honest, it's amazing. More important things to talk about. I don't think this table. Oh, they averaged the results over 3 random seeds. I don't think 3 is enough, but it's better, much better than 1. We have a question in Q&A. So these will have implications for active learning. They do some comparison with active learning, but the way that active learning currently does things is slightly different from this, because the ambiguous samples, maximizing their variability metric, which is the ambiguous samples, is not the same as what active learning does. So yes, I would say that these results might change the way the active learning samples are collected. Does this answer your question, Dwayne? Raise the hand. Okay, let me just give permission to talk. I think you have permission to talk, Dwayne.
Yeah, I was just saying that did answer my question. It's similar enough that it's intriguing. So I like it. Yeah, so thank you.
Okay, good. More notes. So by the end of this section, I bet that most of us were thinking, okay, so I should start building these maps, gathering the ambiguous samples, and save some money on the GPUs. And they try to make sure that this is a correct way to do things, and they realize that there are a few asterisks to keep in mind. So selecting the most ambiguous samples to get the better results is not necessarily true. There are some properties that must be preserved. So in section 4, they built this table where they try to slice the training set according to strategies, either randomly or using the top ambiguous samples. And the plot ends here, and the reason for which the plot ends here is in the text. So if you use a small amount of top ambiguous samples, the performance is actually random. So in this task, because it's a binary choice, it's 50%. So they don't plot it, but it would go down here. So using the top ambiguous samples only works after a certain point. But why? Why do we need 25% of top ambiguous samples and not 15%? What is going on? What is the difference? And in the text, they theorize that when you start having many top ambiguous samples, you will also capture some samples from, let me get them up on screen. You start gathering samples from this region, from the easy to learn region. And they try to confirm that with the plot on the right, this one, where they pick the top 17% ambiguous samples, but replace some of them with easy to learn samples. And they conclude that if they do that, they can use fewer samples and get better performance than the randomly sampled samples with that percentage of sampling rate. So in essence, you need, if you want to have good performance, you need by necessarily samples from this region. You can't get away from it. These samples from this region are the samples that give structure to your model, to what your model is learning and understands. If you don't have them, the model will not be able to pick up the structure and therefore cannot leverage the difficulty of the ambiguous samples to try to learn further. And they argue, not in this section, but I believe in section 7, which is related work, that doing things this way, so having a few easy to learn samples and many ambiguous samples, is similar to curriculum learning. So you start by learning the easy things to pick up the initial structure of your problem, and then you move on to harder challenges. And those harder challenges enable you to distinguish with fine grain what is going on in your problem. So essentially, you can crop the samples with high variability, but if you do so, you need to make sure that you have enough samples from this region. Otherwise, your model will not be able to learn, as they discuss in this section, and that is why they don't show the plot down here. However, if you do so, the top ambiguous samples will get very high performance, especially in out-of-distribution sets, with much less training time. Comment in the chat. I would say that not the structure is learned by easy samples, but the manifold in which the dichotomy is simplest. Yes, probably. We had a few presentations about manifolds a few sessions ago, and I agree with that statement. So the easy samples are probably much easier to linearly separate in their manifold, and so the model can start picking up where to slice that manifold and get a finer resolution as it gets the ambiguous samples. In tables 3 and 4, you'll get very similar results. So if you use ambiguous samples, you'll get nearly or better performance in the in-distribution set, but necessarily better performance in the out-of-distribution set. And they do the same for the SNLI dataset here, where you get the same conclusions. Let me double check if I did not forgot to mention anything. Yeah, so by now we understand better what we should do if we want to train a good model with fewer samples, or perhaps a more generalized model with better generalization capabilities using fewer samples. And they try to extract further conclusions from their map. And to be honest, from sections 5 onwards, I don't agree that much with what they claim, but I'll give you an overview. So in section 5, they theorize that the hard to learn samples are probably mislabeled examples. And to assess that statement, they did the following. They gathered a few high confidence samples, so samples that the model can always get right, and they randomly switched the labels for 100% of the data set that contained high confidence. And then they retrained the whole data set and they measured their metrics again. And what they got is the following. If you swap your high confidence samples by another label, your model will not give as high confidence to those switch samples. And those switch samples would correspond to incorrectly labeled examples. And if you measure the variability, so initially it had 0 variability because it was in the upper left corner, then the variability suddenly starts being all over the place. And by doing this, they claim that this map can easily identify incorrectly labeled samples. My criticism to this experiment is the following. The incorrectly labeled examples in the original dataset could correspond to things that are very hard to label in practice, so they are confusing, ambiguous for the human being. But it's still a structure, so it is not a random label. It is a label that could make sense in the context of that sentence. While in this experiment, they replace the labels by random things. So even though their data sets are simple, so the Winogrand is a binary classification and the SNLI only has 3 classes, I don't think this property will generalize well if you have a data set that has many classes. However, for the particulars of the experiments they executed here, it resulted quite well. So they were able to find a few examples that were incorrectly labeled. So our annotations show that for Winogrand, 77% of the instances predicted as noisy are indeed either mislabeled or ambiguous, compared to only 13% of the ones predicted clean. So this is if this works, this would be a great way to identify incorrect labels. But again, this experiment is on a particular data sets with few classes, so I wouldn't extrapolate this to data sets with more classes. The last bit of the paper, they tried to see if they can use their map as an uncertainty measure. And to do that, they use the SNLI dataset, which, as we can see here, has 5 labels for each example. And they plot the confidence in their map versus the variability in their map versus, in color, the human agreement, the percentage of human agreement. And you get this shape where the samples with high confidence and low variability usually have high human agreement, and the other way around. So samples with low confidence and low variability usually have high human disagreement. So they theorize that their map can also measure the intrinsic uncertainty, which if you read more papers about uncertainty, it's also called aleatoric uncertainty. Again, I'm not entirely confident if their map is that great of a solution to pick up on this, but they noticed these patterns, so they made a section about it. Not too keen on it, to be honest. Another comment in the chat: the applied perturbation to the labels. Oh, so this is regarding the previous section. The applied perturbation to the labels in the training set could increase the generalization. So this model is not really the same anymore. Yes, I would say so. Let me think about your sentence. I think it makes sense. The model is not the same anymore. That is true. So this is not, well, I think what Lev is saying is that this is not an apples for apples comparison. Is that right? So by changing the data set, you are by necessity changing the model, so you can't make a direct comparison between the two. Yes, correct. Okay, good. I agree with that statement, because the models only learn what you give them, and if you change the data, they will learn different things. So yes, I think I've talked about the most important bits. They have also an appendix section with a few more results. Perhaps an interesting thing to see is the last page, which is last page. Okay, sorry, my laptop is a bit slow right now. So they build the map for the SNLI dataset, but using different learners. So figure 1 was with Roberta, which is a very large model, and figure 2, the last figure is with different learners. So the first sub-image is for the bag of words learner. The second figure is for an LSTM. And the last one is for an ESIM, which I don't know what it is. But I suppose it is a better model than an LSTM. And what we can see here is that as we get better learners, this map starts having more of like the curved shape. So what I suppose they are trying to show here is that if you, the conclusions of this paper might not be true if your model is not a strong learner, because the shape of the map changes a little bit. And the position of the samples, of course, will change because they are different models. Still, if you have a strong learner, I believe that this paper is very simple and with perhaps meaningful conclusions. So we can use less data to get similar models. And with this, I conclude the part where I go through the paper. Do you have any questions or comments, really? No questions / comments.
So, I'll ask one question.
Yeah.
Can you hear me?
Yes, Adam. Yes.
Cool. Can you just go back? This is just a little correctness understanding question. The charts are empty in the upper and bottom right corners, and that is because you sort of said it, but if you could just say that again for me to make sure I've got it right. So
sorry,
any of the figure one or figure
my laptop is just froze. I think this PDF is huge for some reason. Yeah, these plots are very heavy. Figure 2. Okay, so there can be no samples up here or down here because so if you have a thing with high variability, it means that it will be jumping. And remember, these metrics only consider the true label. They ignore what is happening in all other classes. So if you have a thing that is with high variability, by necessity, it has to jump between very low values and very high values. So on average, it will be around here in terms of confidence. So if you have a sample with high variability, it has to be in the middle. And if you have a sample with low variability, it has to be either up here or down here. Because if it has no variability, it doesn't change. It has to be always the same thing. And if it has to be always the same thing, it has to be either. I
think you read it wrong. I think you can have low variability, but a probability of say 0.5 throughout. So your confidence would be half, right?
That's true.
That's why maybe something like an entropy or something might be a better measure for some of these things at least. But
sure. So this is kind of my underlying question, just with respect to the metrics there, right? Given that they're doing a projection onto this this two-dimensional space here, and their axes are not independent. So we're losing a lot of discrimination somehow, and it feels like there ought to be a way to use a slightly different measure of some sort so that you get a bit more independence, use more of the space, and be able to discriminate more clearly the cases. I'm not sure. I haven't thought about it enough to think about what a right approach would be. Have you?
I think Arvid's suggestion of using entropy could be a strong candidate, and perhaps measure what is going on the other classes. So it could be that it has low confidence for the correct label, but the other labels, you don't know what's happening there, whether they are always changing epoch after epoch, or if they are static in some configuration. I think that could give some more information to this map, which would allow us to slice better.
I think that might actually be also related to some of the other talks we had earlier about this out-of-distribution sampling, where the model predictions themselves are rather flat over several classes. And that I think is currently not captured at all, which was seen there to be a rather important thing to determine what sort of uncertainty the model actually carries.
That's true. And yes, I was describing this map incorrectly, and good thing you pointed out, Arvid, because as I was describing, so there, which incorrectly, that there could be no values here. And there can be values here. I think the fact that there are no values here in this block means that the model is overfitting, because most of the samples, if you look here, have more than 80% confidence. So this could be like an artifact of the model that perhaps is over-dimensioned for the problem. I don't know. But yes, I think that the fact that these two measures are not independent could hinder the ability to slice the map. But I think the fact that they created a map that kind of works is probably all that is needed for us to start thinking in these terms, to think about new metrics so we can create a better map to better slice the data set. Because to be honest, it's not cool to have to wait a few days for a model to be trained. It's kind of boring.
I'll say also, I really liked the way that it maps to our intuitions, right? That seeing more and more easy examples is not going to be a thing we're going to learn from.
Yes.
Seeing examples that are just too hard isn't going to help us either. And a mix of enough easy ones to make it, to make us not forget what most things look like, and the ambiguous ones to help us, catch the important cases that aren't trivial is, I thought that was nice. And I could imagine it wouldn't be too hard to integrate this into, the early epochs of sort of more challenging tasks. Is pretty straightforward to compute, and it could enable you to then, do a small number of epochs early, develop these measures, cut down your data set, and then continue on training with the reduced training set. Something like that would be, seems very pragmatic to me.
Looking at this paper, one of the first things I thought of is that if you can slice your data set to obtain better models, why not change the slice as you are training? So sort of like a curriculum learning, where you get the difficulty of the curriculum as you are learning.
So you could imagine a training regime where you did a few epochs, adjusted the training set, did a few more, adjusted the training set again, right? Yeah, that would be nice.
You would have to start on the full training set though, wouldn't you, in order to do this?
Yeah, as I said that, it occurred to me that was not possible because you have to use the full training set to figure out what to go for next. Thanks.
But you're right in that a few iterations in, epochs in, you can maybe massively reduce your data set by a third or more.
And even if you, every 10 epochs, you did 5 with the full training set, and then you did 10 with a third, right? Or something like that, you would still reduce the, your training time potentially by, 50%, which wouldn't be a trivial thing to do if you kept kept at least the same level of performance.
Yeah, correct.
One thing that they mentioned in the appendix is that they gather these metrics at an epoch level, but nothing stops them from capturing them at every step. I mean, it would be a pain in terms of computational complexity, but we can have a finer grain capture of these metrics. And similarly, different data sets and different models require a different number of epochs. So this Roberta large classifier, they mentioned that they use 6 to 8 epochs, which is a small number. But perhaps smaller models for MNIST would require, say, 50 epochs.
Mm.
So the rate at which we compute these metrics could also have some effect, in my opinion.
Could that be related to these ensembling or self-ensembling models we had a couple while ago? Because in principle, you could think of, rather than going over several epochs, go over several initiations or initializations of your model and run it over and over again, and you would have like an ensemble of models, and you would probably get similar statistics for the mapping parameters than they would there. Might be interesting to see, because I think there was something about how different epochs are correlated. So one might be able to get slightly improved version by keeping more time between epochs to have truly independent sampling there.
One problem that I would identify with this, as it stands in this paper, is that we need to train the full model before we can slice the model and train a smaller model. So I believe that a straightforward next step would be to attempt to gather this information while training, so you can slice while training at the first time, not having to redo the whole thing again.
And the add-on problem with that is that you have to have the full data set. It's not like we can go out and find examples, easy to learn examples, and then ambiguous to learn samples, and then hard to learn in the way that we build the data set.
Would that make sense to do this, to do boosting? What would be different from normal boosting? I think this would make a lot of sense to do in a boosting sense. So you train the first model, then you gather the perfect subslice, which is a mix between easy to learn and ambiguous. You train the second model, you use these two models to create a new map, and from that new map, you use another model. A problem could be that what the ensemble so far considers as easy to learn might not be easy to learn for a single model, and therefore you might lose the ability to keep doing boosting. But I'm not sure whether this is a thing that could happen or not, but I think it would make sense to at least do a few rounds of boosting. Okay, everyone, so it's nearly 1:30, and this has been a good session. So thank you for all your comments and interventions. I'm going to stop recording and sharing. Stop sharing. Stop recording.